talking about most important processing parameters which can influence the results in terms of coating quality in the class of technology which is said to be plasma spray technology. In addition to what we have already seen, we need to take into care also, that's very important item, particle velocity as a processing parameter more important. Because the particle velocity, as we can understand, it has a very high influence on coating properties such as density, for example, cohesion inside the coatings, that is between particles, oxide levels, in the case we are thinking to air plasma spray, for example, because this is the value, the particle velocity, with which we can calculate for how long the molten, for example, metallic-based particles can see oxygen in the atmosphere if it is present. It has obviously also a very relevant impact on roughness of the coating itself, because the splat mechanisms are controlled by the kinetic energy with which the particles can impinge on the substrate, the stress levels, as well as any eventual phase changes inside the coatings, that is materials composition. And the powder velocity can be controlled, that's a guideline, by changing the mixture between primary and secondary plasma gas, the flow of this gas, obviously, the spray distance, the injection angle, and the carrier gas flow, as well as the spray angle. All these parameters have an influence on the particle velocity. So if you want to make a small resume of the spray parameter influences on coating qualities, we can say, according to what we have discussed, that primary gas, and for primary as well as for secondary, we are going to identify plasma gases. They, primary gas, they are very important for gas and particle velocity. If we increase the gas flow, we increase the particle velocity, so we do have faster particles, and these together led to a reduced travel time through the plasma, that is, less heat is seen by the particles itself. So it must be properly balanced in order to have the desired degree of melting of the particles which are going to be sprayed. Fast plasma, also, they becomes quite hard or more hard or harder to be penetrated by the particles through the injection mechanisms. And if it happens, this means that less particles are injected in the hot area, that is the plume. The typical mixture of primary gases which are going to be used, they see argon and nitrogen. The secondary gas also determines as an influence on the velocity, but mainly is, let me say, influence at the voltage of the current. That is an important parameter in order to understand how much energy we are going to put inside the plume, and thus also conditioning the heating mechanism of the particle itself. So when we are going to choose the plasma gas, we need to take into care which is the amount of heat and velocity transfer to the particles as well as also the gas consumption, that's an economic issue, as well the gun lifetime for the electrodes consuming. The current, when we are going to work with setting the current, not the voltage, it also determines the amounts of energy which is transferred to the plasma plume. Let me say that depends on the materials, but just to give to you an example, there is not so much difference if we are going to spray one special material that is chromium oxide in coating properties, if we are going to use with values of current imposed in the range 80, 800, 1000 ampere with a constant gas flow. But just to tell you that if this is the case, we use the lowest value, that is, we are consuming less energy. But secondary gas flow voltage increases, and therefore also the energy increases in this case. The powder injection is another important parameter. So the arrangement of the nozzles, which are used to inject powders into the plume, that is, for example, the number, that is the pressure, it's important, of the flow transporting the particles itself. And it's important because it is also related with the spray distance, which is another important parameter. As we have seen, as we have already said, the longer the particles spend inside the plume, inside the flame, the more heat they get. So highest degree of melting can be obtained without exceeding, in order to avoid to go inside the evaporation phenomena, which can change because it affects, first of all, low melting elements, can change the coating composition. For the primary gas, the nitrogen is the cheapest plasma gas, and it is widely used because it is inert, that is not able to give rise to chemical reaction to most spraying materials. One materials which cannot be sprayed with with nitrogen is titanium, because titanium has a high affinity with nitrogen, and after recombination in the plume, they could be a reaction between titanium and nitrogen to form nitrides. That means if we want to fabricate a titanium-based coatings, that's not suitable, the use of nitrogen, because we are going to incorporate inside the coatings nitrides, which are different in terms of composition, mechanical properties, and chemical physical properties with respect to the starting titanium. But this opens another window. This is one example for the plasma spray technology, which has been used, because if we are going to use such, in this case, titanium, for example, nitrogen, we can expect to have a subclass of plasma spray technology, which is called RPS techniques, that is reactive plasma spray. In this case, we want the reaction, and so we want the incorporation of nitrides inside the coatings. And thus, if this is desired by the designer, we can think to use, for example, in this case, nitrogen. Argon, instead, is the most favored primary gas. It is used, let's have a remind on the energy diagram picture that we have seen, usually in combination with hydrogen or with helium or with nitrogen, just to increase the energy of the plasma plume. Is quite easy to be ionized, so it's quite easy to form a plasma by using argon. it's an inert gas, so it's less aggressive towards the electrodes and the nozzle. And this applies for argon as well as for all noble gas. It is inert to all spray materials, not giving rise to chemical reaction inside the plume. The plasma gas combination, which are usually used in industry, sees the combination of argon and helium. This combination in the ratio, which are referred to the powder composition, can give colder, we should say, but faster plasma. Argon and hydrogen, which is a mixture, giving us a plasma hotter than with respect to the use of pure argon, that is more hot in the particles. The combination nitrogen plus hydrogen, which gives a hot plasma plume due to the presence of hydrogen, but a little bit slower plasma plume itself, that is the velocity. And so depending on the plasma mixture which is used, for example, and having in mind the effects on temperature and on velocity, we need to select the proper spray distance for these selected materials. This means that if we change the plasma gas combinations and we have in mind to spray the same materials, the spray distance is not the same for all the plasma combination, because there are different effects on heat exchange and velocity exchange on the particle itself. For what it concerns secondary gases, in the secondary gases, hydrogen is very important, but it is also already said before, because it has a very, very important effect on heat transfer properties. I mean, we have higher energy, so we can get other particles, and it can act, that's an important point, also as an antioxidant. That's reducing, also spraying in air the amount of oxides which could be formed, since it's a reducing element. Instead, helium, it has a let me say, a beneficial effects on heat transfer properties to, obviously, from plasma to the particles. And being an inert gas, it is, as for argon, it is inert to spray materials, so no chemical reaction can be started by using helium as secondary gases. And it's usually used, as it has already been said, for high velocity plasma spraying, that, for example, with carbides based composition of powders. The carrier gas flow is important because, as we said, but now we have a picture, because it can affect the way in which the powder is introduced into the plasma plume. If the carrier gas flow is too low, the powder will not enter the plasma flame, and this results in poor powder melting. As well as if the carrier gas flow is too high, we can have a sort of phenomena which is called overshooting, like this. That is, particles can travel across, and again, they cannot experience a good melting, let me say, behavior, giving rise, for example, to unmelted particles which can be incorporated into the coatings, or dust inside the spraying chamber. And so also this parameter must be set, and is set typically by pre-experimental test, depending on the substrate to be coated and on the materials which is feeded here as powders in terms of composition, in terms of average size. If we move to the possibility to have this process of plasma in a confined environment, that is in a chamber like those reported here in this slide, we can open two categories of processes. One we have already, let me say, just defined. It is the so-called vacuum plasma spraying, which can exist also in the variant low pressure plasma spraying or low vacuum plasma spraying, which consists in spraying inside. You see, this is the robot. This orange is the robot. At the end of the robot here, the gun is mounted, which consists the BPS or the variant in spraying in near vacuum or under reduced pressure conditions. And in this case, as we have said before, we are going to reduce the frictional force of the atmosphere because we are going to a lower value of pressure, so the plasma plume will be longer. And this means also that we can have higher resident times of the particles inside the plume, and we need higher spray distance. But is it possible also, and this is an interesting process, to have the variant which is called CAPS, controlled atmosphere plasma spraying, in which we can put inside the chamber not vacuum, not let me say the atmospheric pressure, but we can put elevated pressure up to 4 bar. So we need to we need to evacuate the chamber, that reducing the pressure, and this is the typical value of pressure, which is so you see it's not a very high void level, but it is sufficient to remove all the oxygen inside, and then we fill the chamber. For example, we can fill with an inert gas, argon, or we can fill with a reactive gas, and for example, nitrogen, in order to have the possibility that we already mentioned of the process, which is defined RPS, that is reactive plasma spray. The vacuum plasma spray process, let me say, has some advantages with respect to the standard air plasma spray process, but obviously is more costly because we need a chamber and we need all the pumping unit, we need all the pressure controls. Then we could be limited in terms of size of the component to be coated by the chamber dimensions. But anyway, let me say, one of the most important advantages among those which are listed here, some are also disadvantages, is the possibility to have a slow coating solidification due to being in vacuum, let me say reduced heat transfer after impacts of the particles on the substrate. And this is something beneficial in order to reduce and better control the residual stresses on the fabricated coatings, which in some cases is the basic mechanism on which under working condition coatings can undergo in failure. Here I have reported just for you, these are industrial, let me say, slides, some of the configuration which are existing for the vacuum spray processes. The only thing I want to say to you that this type of gun is the Sulzer Metco gun that we have seen at the beginning. And so we can have different, let me say, configurations, but if you see, apart the last process, which was developed essentially in research and development activities, but let me say, it has not received the real industrial attention for real component fabrication in terms of volume of components which can be considered significant. They are all with a configuration vertical or horizontal and with a pressure range, pressure inside the chamber, which is in the near the value of 50 millibar. Here you have a comparison of these different PPS processes, being the most used, the first one, the one which is really called the vacuum plasma spraying. They can be different in terms of you see the spray distance, in terms of electrical input power, but usually they are the same for what it concerns the coating thickness which can be fabricated, and the value of the deposition rate, which is quite high with respect to those we can and we will experience for thin film coatings technologies, where we can have, we need still to discuss that, but it can anticipate the position rates in terms of thickness per unit time, which is something around micron per hours. In the case of plasma and vacuum, also plasma spray processes, we can have deposition rate which are in the range of millimeters for some minutes. So for minutes would say, so also the productivity is very different. Some applications which are, let me say, not related, but just to tell to you how these technologies can be used and are used in a widespread area. For household appliance, like this one, you see the powder type which is used is a ceramic one, alumina titanium. Here you have the average size of the powders itself. Here you have the most important values of selected processing parameter. You see here working with a plasma gas mixture, which is argon plus helium. Obviously, that's APS, air plasma spraying, because we are spraying and oxide materials. You see here the spray distance, which is around 10 centimeter. And these coatings, which can be realized here, they are coatings giving with a specific micro hardness and specific roughness surface properties of on the base materials, which could be, for example, steel, in order to have anti-stitching behavior of the appliance itself. Another sector I mentioned that in which plasma spraying is used is in the paper industry, analogs and calendar rolls, due to the high wear, let me say, loads that paper is able to put onto the surface with which it comes in contact during the fabrication. Also for the transfer of ink to printing rolls, the possibility to have coatings which is laser engraved, like this one, in which ink can be retained into the special morphology of the coating itself, is very important, as well as the possibility, as we were telling to, as said before, to have wear-resistant surfaces. That's an example of a coatings. In this case, it's a cermet coating in which we do have a metallic phase, which is based on nickel and chromium, and a ceramic phase, which is not a non-oxide ceramic phase, like in the standard cermet materials, but is chromium oxide. And then the coatings in the gas turbines. We have seen also these pictures, just to remember, combustion chamber, blades, that's an important area of application referring to our field of this kind of technology. Let's move a little bit now to the most important, as we have defined last time, process that we can meet in the combustion-based thermal spray technologies, and which is named HVOF, that is high velocity oxygen fuel flame spray. So, which is the basic configuration. In this case, we do also have, also in the case of HVOF, a gun, that depending on the type of technologies which is used, the gun can be a little bit longer than the torch. This is the real name of the gun for the plasma spray technology. And it has a combustion chamber since inside the gun, since the energy is given by combustion. So we need to use a fuel and then the combustion, in order to achieve highest possible temperature, is given by using not air but using oxygen. Then, in most common configuration, we have a differently with respect to the plasma spray technology, an axial injection of powders inside the gun. And obviously also in this case, we do have a gas which is going to transport the powders inside the gun. And so we have the interaction between the powders and the high temperature area due to combustions. And then we have a barrel exit, which is depending on the gas particle velocity, but usually they are supersonic stream. It has a converging, diverging section in order to increase velocity after the combustion step. Also in this case, the torch usually is cooled, and most of time it is cooled by gas, not by water, like in the plasma torch. For what it concerns the basic mechanism, provided that they are different, there are differences in terms of temperature and velocities, as we already have seen, but the basic mechanism of the interaction of the powders with the plume, let's call it also here in this way, are the same. That is, we do have acceleration of the powders, and then we do have melting of the powders itself, or partial melting on the powders, depending on powders composition. So then they are projected on the substrate to be coated. The torch, again, in this case, can be moved by using a robot, and so we can coat layer by layer, also complex, let me say, geometries, complex components in terms of shape. This process, the HVOF, is a process which is carried out only in air. So one thing that we should a little bit discuss is the fact that if we are going to spray metallic-based materials, we could expect, in principle, due to the fact that we have air surrounding our flame here, our plume, we could expect, in principle, some kind of oxidation. But we will see that this can be very, very minimized for the reasons that we will discuss in a moment. Remember that if we want to compare the plasma with the HVOF, we have said that the plasma, due to the high temperature processes, they are essentially in all the variants, but controlled by thermal energy. Instead, if we are talking about HVOF, they are processes which are controlled by kinetic energy, due to the very high particle velocity and thus gas velocity value that we can experience. We set this number in terms of particle velocities. Maximum values can reach around 800 meters per second. For what it concerns the flame velocity, we can experience values corresponding obviously to the maximum particle velocity, which are higher than 2000 meters per second. So very fast process. The maximum flame temperature, depending on the fuel which is used, is around 3000 Celsius, even though usually it is a little bit lower than 3000 Celsius, but not so much. And so again, remember that this process is not the most suitable to fabricate coating starting from high melting point materials, like, for example, ceramic materials, oxide-based ceramic materials, because melting degree obtained is not sufficient. Some examples of coatings, and I will mention, made by ceramic materials using HVOF have been done. But in this case, we need a very strict control on the average size of the particles, which must be of the order of 10-15 micrometers with respect to the standard for the HVOF, which is around 20-25, sometimes 30, because reducing the diameter of the particles, we could expect, and this has been proved, but in any case, the most used technology in this case is plasma, we could expect a sufficient degree of melting of the particles. This has been done, for example, with alumina, not with zirconia, because melting temperature of zirconia around 2700 Celsius is too high, but for alumina, which is a little bit lower than 2000 Celsius as melting temperature, experiments have been done. And the principle of coating formation is just the same of what we have seen for the plasma spray technology. The advantage with respect to the plasma spraying when we can use HVOF is, let me say, put on a double line. First one, that we are not, and we do not need to use this process in a confined environment. So HVOF is always performed in air. And the second one is related to the fact that highest velocities of the particles can lead to us to very low value of porosity inside the coatings. With mass density which can approach 99% of the theoretical density of the materials when fabricated with another technology. Which are the materials which are possible and which are those which are most used? You see here, I have mentioned alumina, but just let me say as experiments, they are typically materials having not very high melting temperature. So pure metals, for example, or metal alloys, or self-fluxing alloys, they are again metal alloys. MCHAIY, which we have discussed because it is the bond coat of the thermal barrier coatings, and cermets, but having as a reinforcing ceramic phase not an oxide, but non-oxide ceramic, typically carbides. In this case, as we have said, but we need to repeat, if we have our particles, which is made by let me say, matrix based, for example, on a metallic alloys like nickel, chromium, just to give an example, and other small ceramic phase, which are, for example, tungsten carbide. So we start from pre-alloyed particles, which can be also fabricated by gas atomization, by mechanical milling, with the methods that we have discussed when we discussed about the sintering technology for ceramic materials. In this case, we are not going to expect to experience any melting of the carbide of the ceramic phase in the cermet materials. What is going to be melted is the metallic phase. Thus, the mechanism for which we can experience the split and then form the coating is related to the presence of a melted phase, which is only the metallic phase. The area of use of this kind of technology, is essentially in order to fabricate hard coatings, that is wear resistant coatings, or corrosion protection coatings. I mentioned also high temperature corrosion protection because this is what is expected as one of the function of a bond coat in a thermal barrier coatings. And the application of this kind of technology is also very wide because it can be used, and it is used in the, let me say, aircraft area, but also in automotive, power plants, gas turbines, paper printing industries, steel industries, etc., etc. Some examples of application of these coatings made by this technology in the aircraft area, we can have functionalization of mid-span dampers, or bushing flange, others, and exhaust flaps. You see here, we have a cermet materials in which the ceramic phase is a carbide base, not the tungsten carbide, but the chromium carbide. Compressor seal rings, in this case, we do have a tungsten carbide in a cobalt matrix, etc., as it is reported here. Apart from, again, it must be mentioned, the MCHAIY coatings, which act as bond coat in a thermal barrier coatings. We have also this area, which is very important, very interesting, to which for which we will have some dedicated slides, but let me anticipate the possibility to use this kind of technology with proper coatings in order to replace hard chrome plating, which is a technology very simple, very easy, but very dangerous for the safety of the operators. For example, for the surface functionalization on landing gears or other aircraft parts. So this, what we have said. In some cases, we can use HVOF also in order to fabricate coatings with proper electrical conductivity. In this case, we are not going to use the powders that we have mentioned before. We are going to use copper, but we need to assure very, very low oxygen content in the coatings. Otherwise, the electrical conductivity of the coating itself will fall in a significant way. Here you have a list of the most common. Then I will leave to you also a table, more detailed, but just to resume, the most common and most typical materials used for the HVOF. So carbides, the tungsten carbide in a cobalt matrix, or in cobalt chromium matrix, or chromium carbide in a nickel chromium matrix. Pure metals for corrosion protection, like aluminum, for example, copper, for the reasons I just mentioned to you before, or steel, again, for corrosion protection, or cobalt-based materials like stellites and triboloid. They are materials, metallic alloys, very hard on the surface. Nickel-based materials also, like Inconel alloy, report coatings can be made by HVOF, as well as MCHAIY, and some very few cases of ceramic like alumina, what I have told to you before. All the peculiarities of the HVOF technologies, if we compare to flame, let me say flame, we have not discussed, is another combustion-based process, very poor in terms of technology, but if you compare with plasma, the most important benefits which can be obtained is the very high bonding between coatings and substrate. We can experience due to the high velocities and the possibility to have the barrel at the exit of the torch, like we have seen in the previous scheme, thus reducing the amount of possible reaction with oxygen, the possibility to also have a reducing, in some cases, that depends on the fuel, environment inside the flame. So we have low oxide metallic coatings. That means the quantity of oxides which can be retained in the coatings is very low for reaction between powders and the atmosphere. Due to high velocity, we have a very high value of resistance of the coatings itself. That is a very good cohesion, very low value of porosity, and this gives to us also the possibility to have suitable values of micro hardness and lower value of roughness of the surface as sprayed, and then the possibility of retain also a very good machining possibility of the coating itself is linked to the fact that most of times we are going to spray not ceramic materials, but we are going to spray metallic base alloys. The problem of oxygen content is very important for the MCHAIY coatings, which are fabricated by HVOF, and the possibility to reduce the oxidation when we make this process as it is done in air is linked to what we have just said. So the high velocity of the particles, so the short dwell time, because we have high kinetic energy, so less time traveling from the exit of the barrel to the surface of the substrate, but the possibility to have a flame composition which is reducing in terms of having in mind the possible chemical reactions, and also the possibility to adopt some tricks like the shrouding of the plasma by using a longer barrel. Shrouding means that the interactions are going to happen inside the barrel where the oxygen is essentially not present. And this is an example you see here of a coatings which have been fabricated by HVOF. In this case, it's a conic acrylic coatings applied. This is an anticipation with hydrogen fluid. The hydrogen is the most reducing environment that we can expect inside the system, and so using hydrogen as fuel, that's for sure. We can have a very limited amount of oxide formation in the metallic base materials, even though we use not air, but we use oxygen for our combustion processes. And this is evidenced by this cross-section of the coatings. In this case, if you see the microstructure is quite uniform. The presence of oxide would have been results in very contrasted particles embedded inside the coatings, and this is not the case. Here, just for you, I have reported, it's quite a long list, so obviously it's not necessary to know. You have just a reference if you need something. The most common powders which are used, commercially speaking, and commercially available, sorry, for HVOF, that's the commercial name. For example, the first one, the amyloid, with the information related to the mesh sides, and the mesh sides is what we have already discussed when we discussed about sintering for ceramic materials with typical properties and application. There are quite many, even for the most common, they are commercially available. The most common are those we have summarized before. So that's another producer, the same producer of the plasma torch, which makes also powders. So there are many producers in the world. These are the most known and the most, let me say, diffused. So they do have a commercial name which never tells to us about the materials composition. So we need to go on the catalog of the producer if we want to well understand which is the composition of a certain named powders for HVOF. Again, that's another part of the table, and so you can have all the, let me say, information and reach them quite easily if you read somewhere that this is an HVOF coating made with iron alloy 2004 powders. So look to the table and you have an idea of what is the powders, which is the composition, and which is the purpose for which that powders and that coatings has been used. These are the list instead of the fuel gases that can be used or can be found for the HVOF. Let me say that generally speaking, each gun is able to work essentially with one type of fuel. So you can have different guns. The process is again HVOF, and it's always HVOF depending on the fuel which is used. So we have the possibility to use hydrogen. We have techniques in which the fuel is methane or ethylene or propane or propylene. This one, the hydrogen-based HVOF system, is those most performing, able to give to us the highest value of flame temperature, able to give to us also the possibility to establish inside the flame, as we said, reducing the environment, thus minimizing eventual oxidation problems for the powders which are fed into the flame itself. We are working with hydrogen, which is a very dangerous gas in this case. So the systems and the plants must have all the security tricks and all the security levels, but this is an engineering problem. It can be easily done, and it is done. Thus, this technology is diffused for the fabrication of coatings. Some applications of the HVOF, I was mentioning it before, the hard chrome replacement. What does it mean? Well, electroplated hard chrome, which is also mentioned as EHC, is the standard process to put on one metallic surface, for example, chromium-based coatings, which is very hard, that is very wear resistance. And the standard procedure involves an electrolytic process from which the deposition of chromium, metallic chromium, onto the surface, onto the substrate, can be obtained by a reducing mechanism which is forced inside this electrolytic bath in which we do have chromium ions, typically 6 plus, which are into the bed, and to which we give electron, thus having a reducing reaction till the formation of CR0, which is the metallic element being deposited onto the workpiece, that is, onto the substrate. This system has a wide range of application, is very well known, used in many industrial fields since about 100 years. It is able to give to us very hard coatings, just reducing wear. In some cases, that depends, also giving a corrosion protection. Is cheap and effective, and the system itself requires a low investment cost if compared, for example, with the HVOF. So that has been, and sometimes it is still used, let me say, the standard solution for fabrication of very highly resistant coatings for wear problem. It is used not only in the industrial area with the purpose that we have just mentioned, because the electrolytic process is also used in order to fabricate decorative coatings. In this case, we have very thin coatings, which are about 2 microns in thickness, even though for what it concerns our interest, we are here in the so-called technical hard chrome plating, in which the thickness are as high as 100 micrometers. You see the typical substrate materials which can be treated or which are treated with this EHC technology. And it has also a very good deposition rate. See here, we can have in an hour the fabrication of coatings with thickness ranging from 10 to 30 microns. Some other features which characterize the hard chromium electrolyte based process. The appearance is the morphology, the color of the surface thus treated is silver. You see here value of hardness very high, reaching 1000 and 100 picars. Remember that silicon oxide, silica, it has as maximum value 1200 picars, and this led to us also very wear resistance together with abrasion resistance. Then these kind of coatings, being essentially metallic, they are very easy to grind, to polish, that's to finish, and can give to us very after mechanical treatment, very low value of final roughness, thus reducing also the friction coefficient and thus giving to us a hard coating onto the surface, reducing the power loss for friction and increasing the lifetime of the component treated, because the damages induced by wear are reduced. Some typical application, you have seen it also on the way, for example, hydraulic cylinders, rotating shafts, landing gears in the aircraft industry, piston, valves, rolls, stainless steel cutlery, household appliance that essentially for decorative purpose. Some cases of applications also in the biomedical area. But which is the problem of this very cheap very simple, highly effective technology. The problem lies here in the use of hexavalent chromium inside the bed, inside the bath, yes, the electrolytic process. And you see here, which are the problems for the safety, for the health, I would say, of the operators, which these hexavalent chromium can cause. And this is already known, a well-known state-of-the-art, let me say, effects. And so the needs to develop or to use coatings which are different from the best hard chromium technology based on hexavalent chromium has started. And there were some experiments based on the same principles, but using not hexavalent chromium, instead using trivalent chromium, but the performance, or well, let me say better, the properties of the fabricated coatings in this way were not essentially comparable to those obtained by the use of hexavalent chromium. And one solution to our chromium plating based on hexavalent chromium is to refer to the use of HVOF coatings. HVOF coatings, we need to select a powder which is able to give to us comparable properties of the thermal spray coatings with those obtained by the electrolytic process. And so the work started, and the aircraft industries was the pioneer in this field. Knowing the advantages as well as the limitation of HVOF, and the solutions which was identified was the use of cermet coatings. And essentially one of the most important solutions is the first one or the second one. You see here the values of hardness which can be reached, for example, with this kind of materials, which are at least 80% in weight in the ceramic phase, being the rest 20% in weight of the metallic phase. But this is sufficient in order to have a suitable split during coating fabrications. And if we just have a look to the hardness values, we are able to reach, apart from the last one, which is not used to this purpose, that's a comparable table, values which are the same and sometimes also higher than those obtained with the hard chromium, based on hexavalent chromium. Here you have a table just to resume one and the other solutions are chrome plating and HVOF. This is a typical, let me say, a gun which is based on the use of hydrogen as fuel. And you see here that for what it concerns the hardness, we can reach also values which are higher than those of the chrome plating. For what it concerns the macro hardness, so we also can have values which are higher than those obtained by hard chrome plating. In terms of porosity, we do not have many, let me say, differences. In terms of bond strength of the coating with the substrate, we have values which are more or less similar. And one which is going to make the difference, and this was one of the elements for which the powder composition has been selected, is the corrosion resistance properties. We can have in terms of fatigue behavior better properties expected by the HVOF with respect to the hard chromium replacement. And well, that's other information. Let's go on. You see here another table of comparisons of properties obtained by chromium plating and cermet, in which we have tungsten carbide, cobalt, but also another metallic phase, which is nickel chromium. If you see here, by comparing, we can achieve the properties and sometimes have also higher value, as we said before, of the chromium plating. And here you have two examples of microstructures. This is the hard chromium, you see here, and we have a thickness which is around, if you look to this bar, around 200 microns. This is the case of tungsten carbide with chromium cobalt matrix. And if you see here, apart from the surface morphology, which is different, obviously, because this is an electroplated, our coatings made by thermal spraying after fabrication, that's not requested, apart from polishing for the hard chromium, but we can achieve easily the same thickness of, obtained by hard chromium placement. And have a look to some other properties in terms, for example, of friction coefficient and wear resistance. This was evaluated according to an American Society of Testing Materials standard, which tells us how to make in a lab scale, wear resistant testing. And if you look to this part of the table, which is going to be referred to materials fabricated, coatings, fabricated by HVOF, and we look to, for example, for the wear resistance, have a look here, wear resistance of these HVOF spray coatings with respect to the wear resistance evaluated in terms of wear traces. Is when the wear traces is going to increase the wear resistance coefficient values, but the longer lifetime of the coatings and as well as in terms of corrosion resistance. So one very common way to test corrosion resistance to the purpose for the aircraft industries is to refer to standard procedures which are based on the so-called salt spray test. I mean, in this case, we put salt on the surface. This is usually sodium chloride. Why sodium chloride? Because we have sodium chloride in the seawater, and most of the aircraft are flying or are near the seawater, or they have the hangar. Think, for example, to the Rome airport, Fiumicino, near the seawater. And if we have a look here to the figures which is given by this procedure of salt spray test in terms of survival of coatings or hours inside the chamber where the salt is sprayed, well, this is the hard chromium. This is the standard tungsten carbide cobalt made by HVOF. This is a nickel chromium carbide made by HVOF, and this is the solution of HVOF spraying tungsten carbide, cobalt, and chromium. See here, we have 86% of tungsten carbide, 10% of cobalt, 4% of chromium. And I think we cannot need to add something, because just having a look, depending obviously on the coating thickness, on the length of the bar, we can see how, in this case, with respect to corrosion resistance, we have different properties depending on the material selected for the HVOF, but we can reach results which are very, very performing if referred to the behavior of components treated on the surface with electrolytic hard chromium. These are some examples of the samples which have been tested. You see here rust, which is formed after the salt spray test. Here, different solution of HVOF coatings. But if you have a look to this, which was the one here best performing with 100 with 400 in this case, together with the powders, which is made only by tungsten carbide and cobalt, responding to this powder type, which is one listed in the table I left to you before, you can just see that the appearance is very, very different. This is after 750 hours of testing, and thus showing the better performance of HVOF. Which is the message? The message is that a better performance can for sure be reached, but not for all the materials composition which can be used for HVOF. So this work, in any case, has been done some years ago, recent years, and so we already have the final testing qualification, and so we know what we can select, what we must select in order to have the best results. And thus, landing gears can be coated in this area. You see, these are HVOF coatings. This is an HVOF coatings. They applied by using solutions which have been identified. Obviously, there is, let me say in this way, some resistance from the industry side to move to this kind of solution, excluding the aircraft industries, because the process is a process more costly. I mean, the HVOF with respect to the simple electrochemical bath, which can be used for classical standard hard chromium replacement. But we do have indication at European level that the hard chromium replacement based on hexavalent chromium is to be completely avoided in order to put all the operators in a safe environment during the working procedure. Other examples of parts which have been coded. This is a 757 main landing gear by HVOF. You see the silver appearance here of the parts which have been coded. Obviously, this means due to what we have seen here, that is due to the roughness of the thermally sprayed coatings after fabrications, that we need, and this has been done, to make the coatings, and then we need also to machine the surface in order to reduce roughness and also in this case the silver appearance. The importance of HVOF in this case is related also to the fact that the HVOF, as we said before, it's a process which is driven by kinetic energy, and so that the coatings which can be fabricated, again, have a look to this microstructure, coatings which can be fabricated, they are very dense in a way which is comparable with those which is obtained by hard chromium, standard hard chromium solution. So this is one field of application of HVOF related to the aircraft industries, which is very important for us. Another example, and if you see here, the materials which are considered as materials to be used are those I have showed to you. They do have the best performance, for example, for the corrosion resistance, is the tungsten carbide 70 cobalt or the tungsten carbide 10 cobalt 4 chromium, which are, as we have seen here, because is this solution, and is this solution in terms of for fabricated coatings the best performing materials to contrast corrosion here due to presence of salt in the environment and evaluated on a lab scale with a salt spray test. Another area in which thermal spraying is very important, and with this we will finish the lesson of today, is the possibility, we anticipated that, to fabricate a special class of coatings which are named abradable coatings. Which is the problem we have discussed qualitatively. Let's have a turbine blade. We know that the turbine blade during the exercise will undergo onto creep deformation. And we remember also that creep deformation is an elastic deformation, that is a permanent deformation, that is an unrecoverable deformation. And so if we have put our attention on the casing and on the top of the blade, we need to leave, let me say, a gap between the end of the blade and the case, just to allow that the creep deformation can happen. Without having failure due to the impact of the blade on the fixed part that is on the casing. And so, since we are able, and we know how to do it, to evaluate with time, at least for the stationary part of the creep, how high will be the plastic and recovered deformation due to creep, the width of the gap between the tip of the blade and the casing segment will be and can be directly related to the lifetime expected in terms of maximum hour of operation. But at the same time, we cannot think to use without any other solution, let me say, a gap which is just calculated on the basis of the maximum elongation, maximum deformation, which is requested to be tolerated for example, 10,000 hours of lifetime of our engine, because it would be so high that the gas coming from the combustion chamber will not interact with the profile of the blade, but will skip through this conduct, and thus we will not have any possibility to generate mechanical power. And so what is done? It is done a solution which is based on the use of abradable coatings, which can be put on the casing, for example, by using, for example, an abrasive blade tip, that is another coating, so that this coating in correspondence with the end of the blade tip can be easily consumed during the working lifetime of the engine, assuring the minimum gap which is able to maintain the rotation of the blade, but cancelling this mechanism for which we will not able to convert the energy coming from the combustion in the combustion chamber of the engine to mechanical energy, which is given by our turbine. And so these coatings must be coatings with a, let me say, a special composition, because they must withstand, depending on the section of the turbine, with the temperatures of the gas phase, but they must be easily abraded, and this is the reasons of abradable coatings, in order to let the rotation of the blade happen without any problem. And what is going to be used? Let's go to see directly. Oh, sorry, to this slide. Depending, you see here on the operating temperature, different stages of the turbine, we have, that's again the commercial number, coating composition which they do have. For example, a metallic phase, cobalt, nickel, chromium, aluminum, yttria. In some cases, also a plastic material, polymer-based materials, and ceramic materials, like this one, which is the most known, that is boron nitride, which acts as a self-lubricating materials, thus allowing also the, let's say, the exfoliation of the coatings, of the abradable coatings, the consumer of the abradable coatings during the working life and working exercise of our blade. And this kind of coatings, in which we can have also ceramic phases, usually are made by plasma. And this is one example of an abradable coatings, and you see all the black parts, which are the mixture of the polymer-based materials and the ceramic materials. And so the spraying and fabrication of abradable coatings, which are for high-performing engines, the standard solution is another field in which plasma spray technology is widely used. And so we are again inside the area of our engines in our aircraft. For what it concerns the engines, you will find, I will not discuss this in the slides I have already put on your Google Drive. Again, some consideration on thermal barrier coatings. We have discussed this many times. This is a small refinement just for your purpose of curiosity. So all this, which has been defined when we discussed about TBC, some other pictures are for you, just for your, let me say, sake of curiosity. But what we have to do, what we had to discuss about thermal barrier coatings, it was already done when we have discussed about this argument. Here you have also some examples of nanostructure. That's the same picture of thermal barrier coatings. And so for what it concerns our discussion on surface engineering technology, with this, with the abradable coatings, we have finished the area of the thick coatings based on plasma and based on HVOF, and we need to discuss another important area, which is the area of thin film coatings based on vapor deposition methods, but we will start from here, from this topic, on next Friday. And for today, it's all. So if there are questions, I'm able to answer. Ok.
Scusi,
Eccoci.
le volevo chiedere una cosa riguardo al drive, perché non so come è possibile, ma non ho accesso alle slide, quindi volevo sapere se magari posso mandare una mail, le chiedo il link.
Sicuramente sì, se non me l'ha già mandata, perché io devo...
Ci ho pensato ora.
Ah no, io devo autorizzare io l'accesso, quindi se lei mi manda una mail, metto tra coloro che possono accedere.
Perfetto, grazie.
Prego. Okay, so see you next Friday. Bye bye to all.